All right, so anytime we have a situation where we're having exponential growth that's occurring as a constant percent increase over time, it can be modeled by this formula. This little a, is the initial amount. R is the percent increase. Make sure you're writing that as a decimal, so you have to move the decimal point. And then T is the time. Okay, we'll be doing a ton with this formula in class, kind of modeling the different things that use exponential growth, but things like, if you have the price of something that's increasing by 5% every so often, or if you have population that's growing by 2% every year, like bacteria in a culture, it'd be exponential growth. So there are tons of things. Viral videos would be another exponential growth if they, the number of people who view it doubles each day or something. So we'll do a lot of these type of things in class. I just want to show you a couple examples of this. So the first U.S. Census was conducted in 1790. The population was almost 4 million. Since then, the U.S. population has grown approximately 2.03% annually. We want to write an equation to draw a graph showing the U.S. population since 1790. Okay, so we're going to use the same graph. So our population, our initial amount is this 3,900, whatever. R in this case is, I don't know if I can squeeze it in here. I'll write it over here. R is 0.0203. As I mentioned before, you have to move that decimal. And now we're going to use that to write our equation. So we have the amount that we have now is 3929214. 1 plus 0.0203. And then T, we don't know how long it is since 1790. I mean, we could calculate anything, but to the T power. And then we can go ahead and add those things in the parentheses. 3929214. 1.0203 to the T. So this is the equation showing the population since 1790. So if you wanted to know the population in 1890, you would plug in 100 for T. 1990, you would plug in 200 for T. One thing that I want to mention, order of operations, you do exponents first. So you may not multiply those two numbers right now and raise it to the T power. You need to leave the equation exactly how it is. All right, let's check out the next one. A college with a graduating class of 4,000 students in the year 2010 predicts that the graduating class will grow 4% each year. Write an exponential function to model the number of students Y in the graduating class after the year, T years after 2010. All right, so we started out at 4,000, so that's our little a. And the rate that we're growing is 4%, so that's 0.04. So when we plug this into our equation, we get 4,000, 1 plus 0.04 to the T power. And we can go ahead and add those things in the parentheses. So 1.04 to the T. That is your equation. And then you can use this equation to make predictions. Like if you want to know what's the expected graduating class in 2020, you would plug in 10 for T, just put that into your calculator and it would give you an answer. Actually, let's go ahead and do that because it's interesting. I know the problem didn't ask for that, but so let's say we wanted to find out about 2020. So you would do A equals 4,000 times 1.04 to the 10th. And then you can put this in your calculator exactly as it appears, because you can't really do this by hand. Make sure your calculator knows to do the exponents first. Well, shoot, I don't have a calculator right here. Let me see if I can get one real quick. Hang on, I want to find a calculator. Okay, I found a calculator. I plugged this in. It was 5,921. So if you plug that into your calculator, just make sure you got the same thing as that. On the next page of your little packet are some questions to try it. So I want you to do those first. Don't watch the next video until you try those first on your own, and then check the next video, okay? So pause, do the problems, and then watch the video.